Hello everybody, I'm Adam. In this problem, what we're going to do is find first the parametric set of equations and then the symmetric set of equations of the line that's going through our point with coordinates -2, 0, and 3 and is parallel to our vector given by v equal to 2 times I plus 4 times j minus 2 times k. And if we can, we're going to write our direction numbers as integers. So, to get started, what we have is our point here at -2, 0, 3. Which we have drawn with our little pink dot. So we'll label this as, say, point P with coordinates -2, 0, and 3. And we have our vector v drawn here, which in component form, looking at just the coefficients in front of our unit vectors, this has components 2, 4, and -2. So our vector v here, drawn with components 2, 4, and -2. And so what we want to do is find the parametric set and the symmetric set of equations of the line going through our point P parallel to this vector v. So something to the effect some line going through our point P, which is parallel to our vector v. Right? And in looking at this, we have everything we need. You need a point on the line, and you need a vector that's parallel to that line. And what we're going to do is consider some other point on the line, call it Q, with, say, generic coordinates x, y, and z. And we're actually thinking of the directed line segment from P to Q as a vector. And what we know, since these two vectors are parallel, we know that the vector from P to Q is some scalar multiple, call it t, times v, where t is some general constant, which we call our parameter. So if we change the value of t, we can change the length of q, essentially making it infinitely long, and an infinitely long line segment essentially makes a line. So from this, we're going to find our parametric set of equations. But first, we can go ahead and find our direction numbers, if you recall that. So our direction numbers come from our direction vector, right, which is the vector parallel to the line we're looking for. So we have v is equal to the vector with components 2, 4, and -2. And generally, we can consider those components as a, b, and c, where the a, b, and c, or the components of v, that's our direction numbers. So we actually get the last part of the question out of the way first. So direction numbers are going to be a is equal to 2, b is equal to 4, and c equals to -2. Okay, now we're going to be using those in just a second. So what we want to find now is our parametric equations. All right. So the parametric equations, we have 3 of them, and we have that they are equal to x equals to x1 plus a times t. And we'll go back and fill in what these values are. We'll just write down the equations first. So x equals x1 plus a times t. Y equals y1 plus b times t. And leave ourselves a little bit of space. Z equals to z1 plus c times t. So the a, the b, and the c, those are our direction numbers. But the x1, y1, and z1, those are the coordinates of our original point that we're given. So our x1, y1, and z1. So finding the set of equations is just equivalent to plugging everything in. So our first equation is going to be x equals to x1, which is -2, plus a, which is 2, times t. And our next y equal to y1. So y1 is 0, so 0 plus bt. b is 4 times t. So y equals 4 times t. And lastly, z equal to z1, where z1 is 3 plus c, which is negative 2t, or 3 minus 2t. Okay, so there's our set of parametric equations. Now our symmetric equations come in the form of x minus x1 over a equal to y minus y1 over b equal to z minus z1 over c, where again, we're just going to plug in our known values. So x minus x1, we have x minus x1 is negative 2 over a, which is 2, and that equals y minus y1, or 0, over b, which is 4, and that's equal to z minus z1, or z minus 3, all over c, which is negative 2. And we can just clean this up a little bit. So let's come this direction. So we're going to have x minus a negative 2, or x plus 2, over 2, equals y minus 0, or just y over 4, equals z minus 3 over negative 2. And there's our symmetric set of equations. Thank you very much.